Don't tell me I said that. All right, so let's look at lenses. All right, guys, you will have a two-lens. You'll have a two-lens problem. That'll be the first thing that you have on there. We can look at a two-lens problem later, but when you come to the test, the very first question is a two-lens problem. Remember, on the two-lens problems, it's not going to be one where you have a virtual object. The lenses will be spaced far apart, and so just keep your P positive. So anyway, with lenses, we have a couple of things. 1 over F is 1 over Q plus 1 over P. M is negative Q over P. Both of these on your equation sheet. And by the way, I've updated the equation sheet to include Chapter 9. So if you haven't looked at it in, I don't know, 4 or 5 days, you should take a look at it because it includes a lot of stuff for Chapter 9. For the lenses, it'll be helpful for you to know the ray diagrams. Although I'll only give you a ray diagram for the first scenario for the convex lens. That's this one when I have my object outside the focal point. But I will ask you other questions about what type of lens does this thing, what type of image does this lens form in this particular scenario. So we have 4 different scenarios for lenses, 3 for the convex, outside the focal point, at the focal point, or inside the focal point. These are my objects. And then I also have the concave. It can be anywhere. This is my object. If it's outside the focal point, I can draw my rays parallel to the axis through the focal point, parallel to the axis. So my object is going to be right here. I can draw a third ray that just goes straight through the center of the lens, like that. Those are really the only ray diagrams that you'll need to know how to draw. You don't need to know how to draw the ray diagrams for the other 3 scenarios. I'll give you a lens, one of the rays will be incorrect, and you just need to pick out which one is incorrect. This is the easiest ray diagram, that's why I gave it to you. But you do need to know what types of images these form. The first one forms a real inverted image. Real images are always inverted because Q would be positive, making M negative. This would make no image at all. And this would make a virtual, upright, bigger image. So my image here would look like this. It's a magnifying glass. Virtual images are always upright because if Q is negative, M is positive. And then for this one, I will have a virtual, upright, bigger image. Virtual, upright, bigger image. It's a lot like the, smaller. Sorry about that. My image is smaller. It's a lot like the convex mirror. The concave lens is a lot like the convex mirror. It does the same stuff. Okay? You'll have some problems. You have a couple problems that are just using the lens equation. But on those, they can be kind of difficult because I might not tell you what kind of lens it is. I might not tell you what kind of image it is. Various things. We can look at some problems about that when we look at the old test. But you'll see questions like that. You also have a 2-lens system. As I told you, that'll be the first one. On the 2-lens systems, you take this is your P1. You find out where your image is. This is your Q1. And then your P2 is this distance. So I'll give you the distance between the lenses, say that's L. To find P2, you say L minus Q1. And then that gives you P2. So you're working 2 problems to find the total magnification. It's the product of the magnification from the first lens times the magnification from the second lens. You should definitely, if you don't know how to do these, you should definitely look at it before Monday because, as I said, that'll be the first question. And I always find that if you do well in the first question, like it just sort of sets the mood right? It's like setting the mood for the whole exam. So if you do well in the first question, I don't know, maybe you don't, maybe this is just me, but I think you do better on the exam. Is that just me? Okay, maybe it's just me. But, all right, you need to know aberrations, spherical and chromatic aberrations. You need to know what causes them. The spherical aberrations occur in lenses and mirrors. Rays that focus from the outer parts of the lens focus there. Rays that focus on the inner parts of the lens will focus at different places. So that's spherical aberrations. In order to get rid of that, you put an aperture. to get rid of that. It just blocks the rays from outside. Chromatic aberrations are due to the fact that the index of refraction is dependent upon wavelength, like that. And so different colors of light bend at different angles. So if I have blue light coming in, see, blue has shorter wavelength, it's going to bend more. It'll look like that. Red light coming in, it'll look like that. Okay, so colors of different, light of different colors will bend at different angles. And to fix this, usually put a concave lens on the front. And it works with the way the light bends. Usually it's a system of lenses is all you really need to know. Okay, so that's chromatic. This is only lenses. This is lenses and mirrors for spherical. All right, there's no refraction in mirrors, so chromatic aberration doesn't occur. That's it, I think, for chapter 8, or chapter 7, rather. In chapter 8, you need to know interference. You need to be able to interpret constructive and destructive interference. Constructive occurs when you have waves that look like this. All right, these would add up to give you a bigger wave. We would say that these are 0 or 360 out of phase. Or we could say that they are 0, 1 wavelength, 2 wavelengths, on and on. So 0 degrees out of phase, 360 degrees out of phase are offset by 0 wavelengths, 1 wavelength, 2 wavelengths. Destructive interference looks like this. When I add these up, I get nothing. We would say that these are 180 degrees out of phase, or a half a wavelength, 3/2 wavelength, 5/2 wavelength, some integer value of half wavelengths. They're offset by a half a wavelength. And then in between, we're only going to do 90 degrees. So if you see something that's not this, that is that it's, gosh, it's really hard to draw. Something that it doesn't quite line up, just assume that this will be 90 degrees out of phase. That means they're offset by a quarter wavelength. Y'all follow what I'm saying? We're only dealing with 3 scenarios. Completely in phase, 0 wavelengths, 1 wavelength, 2 wavelengths, on and on. Completely out of phase, those are half wavelength increments, or 90 degrees out of phase. That means they're a quarter wavelength off. So if you have either total destructive or total constructive, it's a quarter wavelength off. That's 90 degrees out of phase. That comes up both with light and with sound, so you'll see it a couple of times potentially. All right, then the next thing is double slit. So we have 3 things. We have double, single, and diffraction grading. Make sure you get them straight in your mind how to do them, and then I'll show you several different problems that you can have. Let me just lay out the double, single, and diffraction grading, and then I'll show you several different problems that you could have with any one of these 3. With double slit, I have 2 slits. They're separated by a distance d. They produce an interference pattern on a screen. We call the central bright spot our 0th order. This is our 1st order. This is our 2nd order. And it's mirrored on the opposite side. We say d sine theta equals m lambda, where theta, if I'm doing, say, to the 2nd order, this is my angle theta. And then also, if I wanted to know this distance y, which you'll probably have to answer this question, if I want to know that distance y, y is equal to L tan theta. It's just by trig. If this is L, this is theta, then y is equal to L times tan of theta. Remember, TOA, tangent of theta, is opposite over adjacent, y over L. All right, for the single slit diffraction, it's similar but a little bit different. For single slit, instead of having 2 narrow slits, we have 1 wide slit. And we talk about the width of that slit being A. It produces a very similar pattern. Except here, when we describe it, we're going to describe m equal 1 at the first dark spot, m equal 2 there, and on and on. So notice how these are different. With the double slit, the order number gives the bright spot. With single slit, the order number gives the dark spot. We don't talk about the zeroth order at all for single slit. And a sine theta equals m lambda, where here m equals 1, 2, 3, 4, and on and on. Diffraction gradient is just like double slit. It's identical to a double slit. The only difference being is that with your diffraction grading, we don't give D, we instead give the number of lines per distance. So for example, if I give you 10,000 lines per millimeter, D would equal 1 over 10,000, which is what? 0.10 hundredths, thousandths. Isn't that right? 0.0001. That would be in millimeters, or that would be 0.0001 times 10 to the minus 3 meters. That's a good point. Make sure your metric conversions are quick, because you'll have probably a half dozen or more metric conversions that you'll need to do to go into the SI system of meters. So make sure you remember that nano is 10 to the negative 9, micro 10 to the minus 6, milli 10 to the minus 3, and centi is 10 to the minus 2. You'll use those a bunch, so make sure that you can go quickly.
It has to be 1 times 10 to the third.
No, because you go to the left. It would be 0.000001. All right. So those are double, single, and diffraction gradient. Now, different types of problems. Yeah, Taylor? It's just the distance from the 0th order up to the 2nd order. All right. So a couple different things I could ask. I could just say, you know, this is your double slit, d sine theta equals m lambda. I give you everything but say theta, and I ask you for theta. So that would be a pretty easy question. You just plug in all the right answers. Just make sure you know your m, your lambda, and your d. Of course, putting your lambda in meters. You know, I'll give it to you in nanometers, but putting it in meters for that. So sort of a lower order question like that. I could also ask you, like in that previous question, what is the distance on the screen from, say, that fringe up to the 2nd fringe? What is y equal to? So I could ask you that question. In fact, I do ask you that question. I could also ask you, I ask you all these. I could also ask you, what is the highest order? The highest order present. And that's a special case when what is equal to what? When theta is equal to 90, right. So the highest order present, I just let theta equal to 90, so this goes to 1, because the sine of 90 is 1. Are those all the special cases? I think so, yeah. So the distance on the screen, just sort of what is theta, what is d, what is m, and then also what is the highest order present. Okay? So that's chapter 8. I think that's it for chapter 8. Oh, you also need to know for the diffraction pattern, if you look back at the old test, you see this. What is the path length difference in the two rays that form the fringes to give these particular things? So here, for the central bright fringe, the path length difference is 0. They both travel the same distance. Here it's a half a wavelength, so they're out of phase. Here it's 1 wavelength, so they're in phase. 1.5 wavelengths, and it goes on and on. So this is 0. This is a half wavelength. This is 1 wavelength. This is 3/2 wavelength, 2 wavelengths, and it's mirrored on the opposite side. And it goes on until your orders run out. Jocelyn? Okay, so you need to know what is the path length difference that gives a particular bright spot or dark spot on the screen. Going back, Jocelyn asked, I could ask you what is the highest order present, or another way that I could ask that question is how many bright spots? Just what is the number of bright spots? We worked one in class like this, and just be careful that you read it carefully because it'll depend what it says will depend on what the answer is. So let's say, for example, that you calculate the highest order present and you find that it's m equal to 2. Okay? And then if you find m equal 2, but I ask actually what is the number of bright spots, the answer is actually going to be 5. All right, take for example this. This is m equal 2, if that's the highest order present. But if I ask not the highest order present, but how many bright spots there are actually 1, 2, 3, 4, 5. So you double the m and add 1 to it for that central bright fringe. I could ask either way. Just read it carefully, make sure. Does that answer your question? Good question.
So to find any number of bright spots, you would double your m and add 1?
Right, you just double m and add 1 because I'm mirrored on either side, and then I have one in the middle. That's the 0th order.
Did you ask how many dark spots?
No, I'm asking. Never seen that either. Anybody else asking? Because like, you count the dark spot here. I don't know. What do you count this dark spot? Is this a dark spot? I don't know. I'm not sure how you do that. I'll just ask you the number of bright spots. All right. That's it for chapter 8. Chapter 9. Again, stick closely to the homework and the questions that we did in class. Lots of stuff in this chapter. Types of different waves, transverse versus longitudinal. Just know what they do to the medium, right? They cause the medium to move. Transverse causes the medium to move up and down. Longitudinal makes it move side to side. Need to know about the basic properties of waves, the wavelength, the frequency, the period, and the wave speed, and how those are all related. These are on your equation sheet, but v is equal to lambda times f, and then also v is equal to lambda divided by t, because the frequency is 1 over the period. So we had several questions on the concept test and in class and stuff that if I give you one of these or give you some smattering of these, be able to tell me various things about the wave. You'll see a couple of questions like that, just basic wave properties. Don't forget your beats. Talked about this, the frequency of our beats is just the difference between the two frequencies. We had a question or two about this in class and on the concept test. Intensity is probably your biggest thing, that maybe not the biggest thing, but one of the more difficult things. We have two things with intensity. The intensity is power over area, that's 4 pi r squared. Both of these are in the equation sheet. So you have this equation on the equation sheet, and then you have the equation for the area of a sphere on your equation sheet. Remember, if you haven't seen that, you really need to print it out this weekend and take a good close look at what's on that sheet. Also, we need to know intensity level, and that's this 10 log I over I naught. You need to be able to manipulate this, so if I give you I, be able to calculate L, or vice versa, if I give you L, be able to calculate I. Remember, I naught, which I'll give you, is the threshold for hearing. That's that 10 to the minus 12. I'll give you that value. Sometimes, though, you're using this to compare two intensities. You know, by how many decibels is a sound louder than another sound, then I would be one intensity and I naught would be the other intensity that I gave you. Like if I asked you, what is the intensity, what's the difference in intensities level for, say, 50 watts per square meter and 100 watts per square meter? Okay, then you would put 100 here and 50 here, and it would be whatever it is. I don't know what that is right off. Okay? Also remember that 20 decibels, a difference in 20 dB is equivalent to, what is it? 100, right? Yeah, it's 100 times as intense. 30 dB is 1,000 times as intense for the intensity. We talked about that, and you might have a question. Just hopefully that'll be a quick question that you sort of basic knowledge. Yeah. Oh. Yeah, so like if I ask you what is the, I have, say, 50 watts per square meter is my intensity, I1, and I2 is 100 watts per square meter. And I just want to know what is the difference in the intensity level for these two, or what is, how many decibels is this more than this? And I would say 100 over 50, and then solve for L. Okay? So you have one or two questions for that. Doppler effect. Remember Doppler effect, if I have a sound and it's moving toward you, there's the frequency of the source, and then there's you over here, there's the frequency observed, the frequency that you hear. This wave has a certain speed, the velocity of the source has a certain speed as well, and so you can calculate the frequency. And that frequency observed is going to be the frequency of the source times the speed of the wave divided by the speed of the wave plus or minus the speed of the source. You have this equation, and there's actually another equation for when the source, for when the observer is moving, okay? But in this case, we're just going to look at the source moving. The only tricky part here is figuring out if we can use a plus or a minus. You need to ask yourself, is my frequency bigger or smaller? In this case, it's moving towards you. It's like a train coming towards you. Your frequency is bigger, so I'll use a, what, plus or minus here? Minus, right. If this value is bigger than this value, then this has to be smaller than this. Okay? Just use a little common sense as you're thinking through this. I think like in your mind you understand the Doppler effect, or you know the effects of it. Just make sure that the number you calculate jives with what you think it is. Okay? Alright, so that's Doppler effect. Like I said, you have the equation on that, it's just using it properly. Ooh, tubes. Those are kind of hard. Well, they're not that hard, because you need to identify the different harmonics, and you need to be able to calculate their frequency. So we have a couple different scenarios. We have the open-closed tube, and then we have the closed-closed tube. In the open-closed tube, my first harmonic is a quarter wavelength, reflects back on itself. In the closed-closed tube, looks like that, reflects back on itself like that. In this case, I get a quarter wavelength. In this case, I get a half a wavelength. The reason is I'm confined to have a node at a closed end and an antinode at the open end. Node, antinode, node, antinode. And that's why you get this quarter wavelength here and a half wavelength on the closed tube. This, by the way, is the same as a string, right? And it's also the same for open tube. The open tube looks very similar, it's just sort of flipped. I'm not going to draw it. Now, in the second harmonic here, looks like this. Here I get 3 1/4 wavelengths. And my second harmonic over here looks like this. Here I get 2 1/2 wavelengths, or 1 full wavelength. This is the first harmonic for both. This is the second harmonic for both. In these cases, we can find our frequency, NV over 4L, where N is equal to 1, 3, 5, or NV over 2L, where N is equal to 1, 2, 3. These are on your equation sheet, but they're not labeled. So if this isn't labeled open-closed tube, and this isn't labeled closed tube. But you can tell the difference between them because I have a 4 right here. Just remember that I have a quarter wavelength. That's where the 4 comes from. Because in the open-closed tube, I get integer values of quarter wavelengths. Whereas over here, I get 2, which is because I have a wavelength, a half wavelength, for the closed tube. So a couple things I could ask you. I could just show you this picture and say, which harmonic is this? And you would say, well, gosh, I have 3/4 wavelengths, means it's the second harmonic. It's not the third harmonic, it's the second harmonic. It's the next one up from the first. All right? Here, if I ask you what this one is, you'd say, well, that's the first harmonic, because it has 1 1/2 wavelength. This is the second harmonic. The third harmonic has like 3 humps in it. It looks like this. That's the third harmonic, and on and on. So be able to identify the harmonics. And I'm not going to throw up like the 12th harmonic. Just be able to identify the first few harmonics. Okay? And then also be able to calculate the frequency given the wave speed and the length of the tube for a particular harmonic. Okay? Yeah, Jocelyn. Okay, let me just reiterate that. I can't get 2/4 wavelengths into this tube because 2/4 wavelengths would be a half a wavelength, which would put a node and a node at this end. I can't have a node at this end, so my harmonics go by odd valued quarter wavelengths. I have one 1/4 wavelength here, and then in my second harmonic, I have 3 1/4 wavelengths. But it's because I can't have a node right here. That's just not physically possible to have a node at the open end of the tube. So it's kind of tricky. I understand that it's confusing because you go 1 and you think, oh gosh, this should be for the third harmonic, but it's not. It's for the second harmonic. All right, so for n equals 3, it's for the second harmonic. Okay? Is that clear? Is it? Okay. All right. Let's see. Also, we need to know about the tension of a string. The frequency of the tension on the string is 1/2L. This came up a couple places. T over mu. This is my mass per unit length. T is the tension. And L is the length. This comes up with your vocal cords as well as it's like a guitar string. We had a series of questions where we asked, so if you change some of these things, how does it affect the frequency? And then further, how does that affect the wave speed? Make sure you take a look at those questions because you can see them on Monday. And then basic stuff about anatomy and physiology of speech and hearing. You need to know the various parts of the ear and the speech production. Let me just try to sketch it out. So you have the lungs here. The diaphragm is a muscle. The trachea comes up, air comes up the trachea. Then you have, this is the trachea. You have the larynx. Inside the larynx, you have your vocal cords, as well as some other stuff. Can you see that? Yeah, that's vocal cords. And those are the major parts that you need to know for speech production. Okay? And then for the ear, this is the outer part of the ear. It's the auricle. Then you have the ear canal. Then here you have the tympanic membrane. All right, then you have bones. I can't get the shapes right. These are the ossicles. They transfer vibrations from the eardrum to the cochlea. The cochlea is this thing. It transfers those vibrations into an electrical signal, and then it goes away by the nerve, the auditory nerve. Is that everything? Oh, there's also in the inner ear, there's a tube called the eustachian tube. That helps to drain fluid away from your ear. So if you're congested or whatever, it's because, and you can't hear, it's because your eustachian tube is all clogged up. You can Google this. There are lots of pictures online that are better than this. Although I don't know how you can get better than these pictures. Okay, but those are the basic parts. So you just need to know them. I'll give you a picture, be able to identify them. Okay? Know roughly what they do, right? Y'all probably know. A lot of y'all probably know this already, right? Yes. Okay. That's it. let's look at some old tests. Are any particular questions at this moment? No? Okay, well, let's just look at some old tests. If you feel like you got it, you know, that's fine. If you have something else to do, that's fine. Just feel free to get up. They won't be offended. Can I just leave? Is that allowed? No, that's not really allowed. Oh, shit, what's wrong here? Okay, I'm sorry. Give me just a second. It's thinking. Okay, not all the tests have the material that we're doing, but they all have lenses and stuff. So I'm just going to sort of go through. If y'all see any that you want to take a look at, or anything in particular, then just let me know. So, like, for example, this is spring 15. No mirrors on this test, but like a lens here, we have a lens, just sort of basic stuff, asking about the magnification. More lens problems. There's a 2-lens system, which you'll definitely have. Holler out if you want me to work through it. It's okay. Double slit stuff about the human eye, what the human eye does for focal length, how the human eye changes its focal point. The eye one. Okay, well, when you're looking at something far away, your focal point is at your retina, okay? Because your image is always forming on your retina, and if you look at something that's far away, the light rays come in, and they focus at the retina. The focal point never goes behind the retina. So if you look at something close, as I have an object here, I'm going to draw my rays. The focal point will actually be like right here. So if I'm looking at something close, the focal point gets shorter. If I look at something far away, the focal point gets longer. Okay? Just remember, if you look at something far away, the focal point is at the retina, and it never goes behind the retina. Okay? Double slit stuff? Okay, so let's see. Yeah, number 19 is a good problem because, well, it's not trivial. Like, it takes a little work to get to the answer. And you're probably going to see something like this, honestly. So let's work through number 19 here. So I have a double slit. It says it's 1.6 meters. That's my value for L. The distance between the slits is 0.04 millimeters, that's D. And I want to know the distance between the central and the first, that's M. And this is my wavelength. My first order is just to find theta. So I say D sine theta equals M lambda. Theta then is the inverse sine of M lambda over D. That's the inverse sine of M, which is 1. Lambda, which is 630, times 10 to the minus 9. Make sure you get those metric conversions in, because you're going to have to do it a bunch on this upcoming test. And then 0.04, gosh, was it 10 to the what? Milli. Oh, yeah, it's 3. All right, so that tells me what theta is. I don't know my calculator. I can't use this calculator. Oh, I'm sorry. Do you know what it is? Does somebody know what it is? What is it? Okay, yeah, it's a pretty small angle. So 0.9 degrees. I'm sorry, I left my calculator in my office. And then when I find that angle, I say y is equal to L tan theta, which is going to be 1.6 meters times the tan of 0.9, and that should be my answer. .025. So B is the right answer. Okay? You're going to have a problem like that, where I just ask you the distance on the screen between between the central fringe and some other fringe, first, second, third, fourth order, whatever. Y'all could do that today? What if I said, I'll give you 20 points on the test? Would you take it right now? Yeah. No, okay. Okay, here's some more stuff, just the angle for the second order. Remember, we're not going to do any of this stuff with the circular diffraction. Sure. Yeah, you'll probably see one like this. I don't remember, but I'll probably put one on there. Here, this is true for double slit, single slit, or diffraction gradient. It won't matter what you're looking at, but I want to know the path length difference. Goodness. This fringe has 0 path length difference. This has 1 wavelength path length difference. This one then is going to have 2 wavelengths. If I'm looking at the dark spots, this one has a half wavelength. This one has 3 halves wavelengths. This one has 5 halves wavelength. But the answer for this one is going to be 2 wavelengths. Again, it doesn't matter if we're diffraction grading, single slit, or double slit. Okay? It goes back to our interference. How much does the wave have to be offset in order to get total destructive or total constructive? That is this value. If I'm offset by 1 wavelength, I get constructive. If I'm offset by 2 wavelengths, I get constructive. If I'm offset by a half a wavelength, I get destructive. So there should be lambda 0. Okay? Yeah. Look at a lens problem. All right, let's look at this number 10. We might have worked this at some point, but it's still a big problem. Person uses a converging lens. That's a convex lens. So when you see that, we'll need to remember this thing has a positive focal length. If it was a diverging lens, it would have a negative focal length. So F is equal to 10, positive 10. The lens forms a virtual image that's 20 centimeters away. So Q is equal to 20, but it's negative because it says it's a virtual image. And I want to know what is the magnitude of the magnification. If I'm producing a virtual image, you can think about this. That means that my object is in front of the focal point. That means I'm going to produce an image that's bigger. If you remember those 4 scenarios that I gave you, so I can immediately get rid of A, not D. All right, but I need to figure out exactly what it is, so I need to find out P. So I say 1 over 10 equals 1 over P plus 1 over negative 20. So that's 1 over 10 plus 1 over 20 equals 1 over P. So 2 over 20 plus 1 over 20, so P is equal to 20 divided by 3, which is 6.7. And then our magnification is negative Q over P, negative 20 over 6.7. Oh, well, that's going to be 3. So B is the right answer. Okay? We can look at another one. Y'all okay with the double lens problem? Okay. You'll definitely have one of those, so but you just have one like this too. Remember, it's not going to be a funky one where you have a virtual object. So here, recognize that this is P1. I need to find Q1. So I say Q1 is 1 over f1 minus 1 over p1 to the negative 1. That's 1 over 10 minus 1 over 20 to the negative 1. That's 2 over 20 minus 1 over 20, so that's equal to 20. And then I do my magnification. M1 is negative Q1 over P1, negative 20 over 20 is negative 1. Now, my image is going to be 20 centimeters to the right, inverted, and the same height as the object, because my magnification is negative 1. Now, this distance is 30 centimeters. That's going to be P2. So, I do Q2 is 1 over F2, that's 1 over 15, minus 1 over 30. That's equal to 30. 2 over 30 minus 1 over 30 is 1 over 30, inverse is 30. And then M2 negative 30 over 30 are negative 1. And so my next image is going to be 30 centimeters to the right over here. It's going to be inverted from what it was here and same size. So their final image is going to have a total magnification of this times this, or it's going to be plus 1. All right, it's going to be the same size as the original object. Or I could ask you, where is that final image, in which case you would say 30 centimeters to the right of the second lens. Taylor?
So how did you get, like, why, so for P2, you just subtract 15 as well?
Right. So this distance we found was 20 right here. And so this becomes my new object. So this object is now 50 minus 20 centimeters. Right, so that's your old, it's not a trick, that's just something.
Oh, so the other side is Q. Where the first lens is?
Right here, you mean? Yeah, this value is Q1. It's what you calculate. And then this value is 50 minus Q1. All right? So that's problem number 1. But it's very similar, just different numbers. Huh?
The image from the first lens is the object for the second lens.
That's right. The image from the first lens is the object for the second lens. Okay. Everybody get that? Right? Okay. What else, y'all? Brian? Okay, hold on. Okay, so I have 2 waves. You're not going to see this exact problem, but you'll see some that are similar to it, so you do need to understand. I have 2 waves. They start here. They're in phase. So when they travel over to here, they're still going to be in phase. So if I imagine, these 2 waves, they start out like this. So if they were to combine here, you'd get total constructive interference because they'd be in phase. Similarly, when they get over here, they're still in phase. Okay? However, one of them stops there at the house, and then the other one keeps going and travels a certain distance. So it's sort of like what we had with double slit diffraction, where I have 2 waves that are traveling 2 separate distances, and one of them travels a little bit extra distance. We call that the path length difference, PD. So what I need to find out here is, what is my path length difference for this extra wave? How much extra did it travel? And if it traveled a full wavelength extra, then I'm going to get constructive interference. If it traveled a half wavelength extra, we're going to get destructive interference. Want to figure out what is this extra distance. Now, let's see, we're looking for it to get destructive interference. In order for it to get destructive interference, this extra distance has to be a half a wavelength. Y'all follow me on that? Destructive interference means that my 2 waves are offset by a half a wavelength. That means the path length difference is a half a wavelength. If I have 2 waves that are offset by a half a wavelength, they look like that. Peaks line up with the troughs and they cancel out. So in order for this extra distance to be a half wavelength, well, let's see, a half wavelength is 600 meters, so that would be 300 meters, because the wavelength of these waves is 600 meters. So that means my second wave has to travel an extra 300 meters. And so the answer is 150. The reason it's 150 is that for this second wave to travel an extra 300 meters, it travels 150 and another 150, or 300 meters. Again, you're not going to see a problem exactly like this, but you do need to understand how when these waves travel this extra distance, that's when they start to cancel out, or you can get constructive or destructive. Depending upon how they travel an extra distance, that's a half wavelength, that's destructive, or a full wavelength, that's constructive. Full wavelength, half wavelength, it cancels out. Does that help a little bit?
Also, I mentioned 250 is more of the interference patterns. So,
Yeah.
that would be 1
That's right. That would be 1/2. Because here I have 0 wavelengths. This is a half a wavelength difference. That's just like the mountain problem. To get destructive interference, I have a path length difference of a half a wavelength. This would be 1, 1.5, 2, 2.5, 3, 3.5, on and on. Anytime I get a dark spot, anytime I get destructive interference, that's a half wavelength, or some increment of a half wavelength. 1, 1/2 wavelength, 2, 1/2, or excuse me, 1 1/2 wavelengths, 1.5 wavelengths, 2.5 wavelengths, 3.5 wavelengths. Okay? Because I have 2 half wavelengths, that's a full wavelength, that's constant.
So for dark spots, you use that, for light spots, you use
Full wavelengths, right?
I was confused when you were seeing these problems.
Okay, I'll pull those up. Those are similar. Anything about this? Okay, we can come back to it, but Abby asked about the concept tests are on the website, by the way. Third page?
That one and then the back.
This one right here. I know this was y'all didn't like this question. I like it, but it's not on the test. But you could see a question where I give you like a couple of waveforms, kind of like what we did before with the light, and ask you what happens if you add up these waveforms. And that was sort of what we do in here, but it was just a little more complicated. You had to figure out where it was in 6 seconds. And this first one, if it's traveling at 1 meter per second, in 6 seconds, it's going to be 6 meters away. So if I start here, 6 meters away is right here. And so my wave there would be in that position after 6 seconds. All right, and then over here, if I start here, 6 meters away is going to be right here. So it's going to be, it'll look like that. So my 2 waves will be at that position. And that's really what you need to know, is to be able to take 2 waveforms like this and figure out what will they look like. I think are you okay with that?
Yeah, okay.
Like if I take these 2 waveforms, they add up to this. Because I can imagine like here, I have 2 places that will add up to give me a position up here. I have 2 values, the red line and the blue line, that combine to give me a bigger line up top. And that happens all the way across so that the resultant wave looks like this. Okay?
The one that's like,
This one? Okay, well, this is for our open tube. So F is equal to mv over 2L. And open is just like a closed. if I have standing waves at 300 hertz and 400 hertz, this is going to be for my third harmonic and my fourth harmonic. That is, for the third, it would be 3 times 100, 4 times 100, and so the second harmonic has to be 200.
I'm an idiot.
You're not an idiot. Sometimes I'm an idiot, but you're definitely not. Okay? What else, folks? Works out of time. All right. Well, we'll call it off there. I'll be around Monday morning if y'all need help. I'll get out of my car. All right. Have a great weekend.